Thank you very much for coming today. Today I have the pleasure of introducing Leif Olmanson. He's the researcher at the Water Resources Center here at the University of Minnesota.
Forest Resource Department.
Well, sorry, at the Forest Resource Department, but yeah.
And I work
so
with
he works a lot in the area of remote sensing, and has had some projects where they're trying to quantify the quality of light using remote sensing techniques. So that's what the topic of his presentation can be about.
Okay. So I'm actually one of the first graduates from the Water Resources Science program here at the University of Minnesota. So welcome all of you prospective students and water resource science students that are currently doing it. So I'm going to talk about the work we've been doing for quite a while using remote sensing for water quality monitoring in Minnesota, and more specifically how we're taking the procedures that we've developed over 20 years of research and implementing in an automated high performance computing environment, and then give you a little bit of background on our water clarity and then the color dissolved organic matter mapping that we've been doing, give you some trends and stuff like that we've been doing. So what we've been doing is we have systems that are out there regularly collecting field data, Secchi measurements on lakes. At the same time, we have the satellites regularly collecting satellite imagery. So what we do is we find good clear imagery from a late summer index period, the time when algae will be at its maximum and when the water clarity will be at its minimum. We take that imagery, find data within a few days of that image, make a model of that relationship, apply that back to all the lakes on an image, do that for enough imagery to come up with the water clarity for the whole state. So far, using that methodology, we've completed 9 statewide assessments since 1975, and over 10,000 lakes are included in each of these assessments. And for that stuff, we've been using Landsat imagery. We've used it for analysis of spatial and temporal trends and causal factors. And this thing we did actually back in 2001, so almost 20 years ago, is we made all of that data available in a Google Earth-like format web browser where you could get information about your lakes. There's a URL right down here. You can zoom in, get information about lakes. You can zoom out like this area, get information for all lakes in the area, or you could go to the whole state and get information about all the lakes in the state. So we just recently migrated that to an ArcGIS server, and then we updated it with some more recent data, so we have to kind of maintain a 5-year interval. The 5-year interval has been great. It's been very popular. We have thousands of visitors coming to get information about other lakes on our site monthly. But if we really want to improve fisheries and lake management, we need more water quality variables. We need it more often. And that's where we're heading with some of these new satellite systems that we have. We have sensors with higher spatial, spectral, temporal, and radiometric resolution. So not only can we map water clarity, we can map factors that control water clarity, things like the chlorophyll, the suspended solids, and then the color dissolved organic matter. So if we look at some of these sensors, we have this one over here, the Landsat. That's launched in 2013. Landsat 8, it was a much improved solid state sensor compared to the old imagery with the scan line correctors and stuff like that. It was much cleaner imagery than we've had in the past. Very good data set. Every 16-day revisit with one satellite. Landsat is going to be launching another one in January. So we'll actually have 2 of them, so 8-day revisit with that. Sentinel-2 is a European Space Agency satellite. It's a little bit higher spatial resolution and more spectral bands and stuff, which I'll talk about in a second here. That's 10-day revisit for 1 satellite, 5 days for 2 satellites. With the overlap area of these, we're getting imagery every 2 to 3 days. With cloud cover, we expect to get about a normal weather condition. If we ever get that again, we expect to have imagery every couple weeks that we can use for water quality assessments. So if we look at the spectra down here, this is a characteristic reflected spectra. So this is kind of a simplified diversity of the waters in Minnesota. If we're having algeotrophic, very clear water, you're just going to have this big peak here about 550. Once you get chlorophyll in here, you're going to have this peak at about 705 due to the algal cells. Absorption due to photosynthesis about 670. And then there's this other absorption trough, and that's due to the phycocyanin, so indicator of cyanobacteria and potential harmful algal blooms. So that's an important band. Color dissolved organic matter, if you're not familiar, it's basically the brown stuff in the water, tannin staining up in the boundary waters or such. So very dark water, absorption characteristic. And so if you have nothing else in there, you're gonna have this very flat spectrum. There's not much to it. Once you add some chlorophyll or sediment, then it's gonna be more, it's gonna absorb, the CDOM absorbs very strongly in the shorter wavelengths, and that decreases as it gets longer. So the yellow one here would be a comparison of something with chlorophyll and CDOM in it. And you can see it's not really affected up in this red edge band, but you can see that the shorter wavelengths are all pulled down. This would be a sediment with lots of CDOM in it too, and you can see how that affects that. If it's just sediment, it's going to be more continuous up here without the absorption characteristics. So if you look at the spectral bands down here, the Landsat satellite, and then Sentinel-2, and then the Sentinel-3 satellite. With the Landsat, you're missing this red edge band right here that's picking up this important characteristic. So that's very important for mapping chlorophyll. And so with this Landsat, you're not going to be able to get chlorophyll quite as well as you would with the Sentinel-2 satellite. The Sentinel-2 has that, and then also the Sentinel-3. Sentinel-3, I don't have a picture of that, but it's basically it's more of an ocean scale satellite, so it's 300 meter pixels. So can't do all lakes in the state of Minnesota, but it can do probably about 900, so 150 hectares or larger. The other thing with that Sentinel-3 important band, it's got that C620, which could be used for the phycocyanin, for the harmful algal blooms. Now that we have all this imagery, before we did every 5 years, we did it kind of manually. It took a lot of work to link up the data and stuff, and a lot of processing, but every 5 years was manageable. Now with data every couple of weeks, it really isn't going to happen. So we've been using a lot more cloud-based and image processing with the Google Earth Engine. Here's a paper, Ben Page in the back corner there, lead author on, and basically a procedure for actually processing the imagery. And that's how we've done our last few assessments here that I'll talk about later on in the talk. Let's see. The other thing we're doing, so we can do it in Google Earth Engine. We're also implementing this on the Minnesota Supercomputing Institute computers, and we're pretty well along on that. And I'll give you a little bit more background on that here. So we have basically have all this data that's being collected. It's freely available. So there's data centers in Europe and then at USGS in Sioux Falls, South Dakota that store the data. So pretty quickly, pretty much the same day or next day for sure, you're going to have this imagery available. We can download it, machine access right to the Minnesota Supercomputing Institute. Once we have that, then we can start processing it. For the processing, pre-processing, we're doing atmospheric correction, correcting all the imagery so it's consistent from one image to another, getting rid of all the terrestrial features. We just want to deal with the water, and then getting rid of the haze and clouds. Once we have clear pixels, water pixels, we can apply our water quality models and then put them into a lake browser. For the process of getting this stuff done for our project, we're in the tweaking stuff of this. We're just getting everything fine-tuned, and we're working on our lake browser. It's a big undertaking to go from data every 5 years, where you have multiple maps at 5-year intervals, to every couple of weeks, and it changes where they're going to be all the time. So it's a little bit different animal, and we're working out the details on that right now. Okay, so Next thing we'll look at is atmospheric correction, the way we're able to do this automatically. With the previous method, we actually calibrate each image individually. And so we could use field data, would have field data link it up. But if you're going to an automated system, you really can't do that. You don't have the time to wait for the data to come in and to do it. We want to have this quickly available. So we need to do atmospheric correction. And basically what atmospheric correction is it's taking the effects from the atmosphere. So on the right up there, that's what you would expect from what, this is what is at the satellite. So the top of atmosphere, so that's what the satellite sees. And that includes all the atmospheric concerns here. So what we want to do is we want to pull it down to what you'd expect on the ground. And so with that, once we have that, so in that, we have tested lots of different atmospheric corrections, and every one of them will give you a different result. So they're not coming up with the same result, and some are better than others. And the big thing with atmospheric correction is they're all under development, or many of them are under development, so they keep changing. So if you build a model, it could change on you. So that's something to worry about. We actually have our own, with that paper was the main one. That's Ben's atmospheric correction for master's thesis. And that's the one we've been using. And the reason why he's here is because I was testing it and it worked out better than anything else we had, which we'll see here in a second. One thing with atmospheric correction, it does not remove the clouds, thin clouds, haze, or shadows, the cloud shadows. And so those have to be removed other ways. Okay, so here's our data set we use for our comparison of the different atmospheric correction algorithms. And we had lots of Secchi disks within 1 day of an image. And then we had some in situ spectra using the spectrometer and collecting field samples and measurements. So here's this data set is from looking at CDOM. So we kind of targeted some of the most optically complex lakes in the state, for CDOM at least. So there's a lot of lakes with a lot of chlorophyll and CDOM in them, and then some very high CDOM waters, as well as a lot of fairly lower level chlorophyll levels, but a lot of them as well. So we had quite a range of conditions. I've tried to make it obvious. The red and the brown ones are high CDOM, and the green and the blue are more chlorophyll dominated waters with different levels, but the levels aren't all that high, except for some of the CDOM dominated waters. And then they got them sorted by CDOM there. So with these, we've resampled that set. So you have this very complex set. And now when you go just to Landsat bands, it makes it fairly simple because there's kind of limited bands. But this is what we come up with. That's the in situ data. And then there's the aero surface reflectance, which also works pretty good. And then here's the main, and then the C2RC. These are the ones that actually, out of that whole list, that actually performed really well. And so those are the ones we're going to look at a little closer here. So here we did the mean absolute % error on these samples. And what we find is these ones actually work pretty good. So the error is around, around 40 to 120 or so % error. Which is actually pretty good, but you can see they are all a little bit different. The C2RCC actually seems to fit fairly well, but they actually use a fitting method that actually tries to fit it to what the spectra would be expected to. So it's kind of made to make it look good on here, and which we'll see in a little bit here. In real life, it might not work as well as it is. The other one, the main, works a little bit better than the surface reflectance on this data set. So if we look a little deeper at looking at spectra for each of these bands now, again, the brown ones are the high CDOM. If we look at these, we find that these high CDOM waters, so we have very optically complex lakes. We're looking at lots of these high CDOM waters. There's a lot more error in these high CDOM waters than there is in the other lakes. So we find a lot more error there. The low chlorophyll, low CDOM lakes have the lowest error. So if you're looking at ocean water, algotrophic waters, you're going to probably be able to get a better atmospheric correction. So the ocean folks have had it pretty easy. with atmospheric correction, whereas inland lakes are a lot more difficult. So what really matters is how consistent these atmospheric corrections work from one image to another. So here we have 3 different dates of imagery with a bunch of field data that we're looking at. And we've developed models for all of these atmospheric correction methods. Using that, we find with the top of atmosphere, actually it works pretty well. 0.83 for that. I tried this back a few years, about 10 years ago. I have a paper where we compared some atmospheric corrections, and top of atmosphere would be like 0.85. Once you do the atmospheric correction, would be about 0.5. So it removed a lot of information from the imagery. That is not the case anymore. They all seem to perform much better than that today, and some of them perform really well. So here we have the aero surface reflectance, and then the main. Both of them actually perform as good or better actually than the top of atmosphere, which is kind of, I would think, the baseline, what you expect. The Aeros ARD is actually an older version of the surface reflectance. It's the same method that's used here, but it's an older version, and that's kind of to compare. When we first did our first CDOM maps, we used the older surface reflectance. When we wanted to make another map, what we found is the atmospheric correction had changed enough where it actually threw our model off when we tried to create maps with it again. So that is kind of the warning story of, you know, if you're using atmospheric correction, know what you're getting and know if it's going to be changing. For these other ones, the atrium, that's the one that had like so those other errors were like around 140 to 100%. That one was over 2,000, as well as some of these others were pretty high errors on some of them. The C2RCC, which worked really good using that fitting method in the spectra, is actually one of the worst ones when we're applying it to actual imagery over 3 different dates. And you can see it's not consistent from one image to another with that fitting method that they use. The Acolyte and the CDAS all had negative values, so I actually had to rescale the data just to make it work. And then they had a lot of missing pixels in that, so that didn't work as well either. So anyhow, so we're using main for our processing. This would be the top of atmosphere, and so basically with main we're able to pull it down. So those blue bands where there's more effect in the shorter wavelengths, and so that pulls it to where it's supposed to be, and you can see how it works really well there. For cloud masking, clouds themselves over terrestrial areas are actually fairly easy to identify, except for over snow. So white puffy thing versus the red is pretty easy to identify. So there are some good cloud masks out there, and for identifying the clouds. For the shadows, what they do is when you have you know where the cloud is, then you use the angle of the satellite and then the sun angle, and you use geometry to project down the cloud or the shadow location, and then mask the whole thing. These work okay. They seem to work pretty good for land features. Once we get into water, they're not good enough. What we find is there's a lot of artifacts from more thin clouds or haze in the red areas. So here we're looking at the thermal band and the blue band to just see the temperature. You can see there's a difference in temperature there, and that's due to the haze. And so we've come up with a different threshold method to actually mask out these things, and that's one of the things that we're testing now to make this work over all seasons. If you do apply those models to the lake pixels, these are lakes, but they're classified as yellow where they should really be blue there, so you can see how much it affects the results. So it's really important to get those residual effects of the atmosphere out of there. Okay, so now we have these different sensors we have a bunch of different models we've developed. For Landsat, we can do water clarity and the CDOM, the color dissolved organic matters. There aren't really any sharp peaks that we're doing with the CDOM. It's very consistent, and water clarity has worked really well. The Landsat 8 works as well as the Sentinel 2, and actually a little bit better in some cases because it's a little bit better radiometric, better calibrated sensor than the Sentinel satellite. For chlorophyll, the Sentinel-2 is a big improvement with that red edge band. So with that, so from the perspective students, how many of you guys are familiar with, everyone who's familiar with Minnesota, or anyone from out of state? Couple, okay. So Minnesota is actually a very diverse state. We have 7 different ecoregions. We have the agricultural ecoregions on the western and southern Minnesota here. And then we have the land of Paul Bunyan and Babe the Blue Ox up here in northern Minnesota, where we have a lot of lakes, wetlands, and forest. And then we have the transitional zone, the North Central Hardwood Forest ecoregion, which has a kind of a mixture of agriculture and also the wetlands, lakes, and forests. And then there's the driftless area that was not touched by the last glacial. So it's quite a bit different than the other areas. And it actually doesn't have any natural lakes in it. So here, and also Minnesota has been kind of an early adapter to actually monitoring our lakes. This is the Lagos data base, and you can see Minnesota started out right away collecting lots of data. So we have a lot of data, and there's not a lot of areas that don't really have data. So a lot of the models that have been developed for water quality have actually been theoretical, and they haven't been validated or calibrated with anything. So, you know, it's hard to say that they're wrong if you're don't have any data to say that they're not. But the ones that I've seen haven't worked all that well in Minnesota when they apply them here. So we have lots of data, and that's kind of the thing that has really helped a lot, is to have something to go to do these with. So now we're going to use those methodology for water clarity in Minnesota. So up to 2008, every image was actually calibrated individually. 2011, 2015, we used our automated methods in Google Earth Engine and did a regional algorithm for water clarity and applied that to every image, the same model to every image, using the main atmospheric correction. So if we look at the different ecoregions here, so we have the northern lakes and forests over here, have some of the best water clarity. So that's Paul Bunyan land up here. Lots of lakes. The next one would be the northern lakes and forest, northern Minnesota wetlands up here. And then we'd have the north central hardwood forest for kind of a ranking for water clarity. The ecoregions with the most lakes are the north central hardwood forest and the northern lakes and forest ecoregions. So and then we get, for the rest of them, we have the lower water clarities in the agricultural ecoregions, and these ones down here. So that we're looking at trends. We're looking at trends from 1985 to 2015, and I'm going to go back one slide. So I'm going to explain this. The legend here, I added the TSI, Trophic State Index. The Trophic State Index was actually developed at the University of Minnesota in Carson, with the paper he did at the, I think it was somebody in the mid-70s. But basically, it's the TSI, Trophic State Index. It's actually used a lot in lake management, and it's basically a logarithmic transformation of Secchi disk, chlorophyll, and phosphorus. And the idea of it, if you have this much phosphorus in the lake, you're going to grow this much algae, and it's going to have this Secchi disk. And that's kind of the idea. So all those numbers should line up the same. So a 40, that all line up that way. It does not work in practice that well, but exactly, but it does give you the kind of idea of it. And the reason I use it here is because 10 TSI units is a doubling or halving of algal biomass. So, or a doubling or halving of the Secchi disk measurement. So it's a good way of comparing different lakes with different trophic state. So if you have a very clear lake, maybe you have 10-meter Secchi disk, and it changes by a meter that's probably not really that big of a deal, that big of a change. You wouldn't even hardly notice it. But if you have a 6 foot or 2 meter water clarity and it goes down to 1 meter, you're probably going to notice that. You're going to see some effects from that. So by doing TSI, those differences can be seen easier. So that's what I have here is I've quantified the change in TSI units. The negative TSI units would be improving water clarity, and the positive would be decreasing water clarity. So doubling of algal biomass, halving of the Secchi disk as we go up. So what you find in the agricultural ecoregions is there's a lot more decreasing water quality lakes than there is improving water clarity lakes. If we get up into the Minnesota or northern Minnesota wetlands and the lakes and forest ecoregions, unfortunately, there's actually an impact there too. There's actually more decreasing water clarity than improving water clarity, which is kind of disturbing because that's kind of our pristine area of the state. We don't have a lot of agriculture and there's not a lot impacts from the ground. So that's a little bit disturbing and different than we saw 10 years ago when we did this. Whether you have northern lakes, north central harbor forest, it's kind of a mixed bag of both can go in each way. Dripless area, big improvements down there. And my hunch is it's probably due to the hydrology, which you'll probably notice in a second here. So let's take another look at that, make it a little bit more obvious. So the red and the orange are decreasing, and the blue ones are the improving water clarity. You can see there's a big difference, big change, a lot of decreasing water clarity in the agricultural areas, plus in the northern Minnesota, which is disturbing to me. North central hardwood forest, mixed bag, and then improving out here. So what we have is we have 16.2% of our lakes are changing greater than 10 TU standards. So they're changing by either doubling or having an algal biomass. 4.6% have increased water clarity, whereas about 9.3% have decreased water clarity. So a lot more decreasing there. If we look at a little bit different delineations, so 10 to 5, so not quite as much as doubling, but still, a big change. We find that it's 22.6% of lakes have changed that much. 9.2 have increased, and 13.4% have decreased water clarity. So more decreasing again. If we take a look at the chart here to what lakes are changing, it looks like there's a lot of the large lakes are changing, getting worse, as well as a lot of these others. A little bit, so it's kind of a mixed bag. The size really doesn't seem to matter that much for that. The wetland type, the type 5 would be the deeper ones you think of lakes. The type 3 and 4 would be shallower, and it seems like everything's kind of decreasing. So it's not really a big identifying here. It's just the shallow, deep, shallow small lakes or something like last time we did this we have a paper out that actually that's what the case was back when we did this for 2005. So what we did notice, we took a look at this period and look at the temperature and precipitation for August to September. That's what the late summer index period we're using for the study. We found there's a 3 degree Fahrenheit increase in temperature over this period. And that is probably going to, could attribute to the increased algal blooms in this area. If we look at the precipitation, there's almost a little minor decrease maybe, but the big thing you'll see are these wild swings from dry to wet periods over this period. So there's some kind of crazy weather, which I don't know if you've been living here in Minnesota, you've kind of noticed some of the weather has been a little wacky. Winter outfield sampling. 2016 was a very challenging year with lots of big storm events and trees down. We had crews that were stuck up at the Hubachek research station up by Ely. So and another one of our colleagues, Nima, and then his colleague Jeff Ho wrote this paper in Nature a few months ago, or Yeah, so but without basically they found a similar thing globally, but out of the 112 million lakes in the world, they studied 71 of them, but they used the whole Landsat record. So anyhow, so we found the same thing as what they found here. So, and the big thing, if it is temperature, unless there's a decrease in temperature, this is probably going to continue to increase because there's really not a lot of BMPs or something you can implement in these forested areas. So let's switch to color dissolved organic matter. So how many are you familiar with color dissolved organic matter? Anybody? We get one? Okay. So anyone up in boundary waters, you see all the brown water? It's very, these nice lakes, but the water's really brown. It's due to the organic material, typically like in a forested wetland or wetlands itself when you have lots of organic material. It's kind of like putting your tea bag into hot water, it turns the water brown. And so that's kind of what we're seeing here. There's up in the northern lakes and forest, there's lots of organic material and lots of water sitting around for this to happen. So why is it important? The color dissolved organic matter is increasing in many areas. We have the dissolved organic matter is important for denitrification of our waters. It attenuates the solar radiation, so it controls the temperature and stratification. So if you ever swim in one of these really brown lakes, it's a nice sunny day, it'll be nice and warm on the surface, but you get your fingers down or your step down, it's really cold, really close. The thermocline is really close to the surface. It reduces the hypolinitic oxygen, which could be harmful to cold water fish. It suppresses the primary production, and it mitigates the transfer of contaminants, things like mercury into fish. So if you have these lakes typically have higher mercury in their fish. And then the big thing would, another cost would be the water treatment, where you have, if you're going to use these for drinking water sources, you need to treat it. It's going to cost a lot more chemicals. You're going to have a lot of harmful byproducts from that process, and then it'll fall membrane. So there's a lot of extra costs for that. And then it's needed for global scale models of carbon cycling. So with that, we've been doing this for a number of years. When we first started working on this, there really wasn't any field data available. So we started collecting it, and then we started working with collaborators to collect it. So Pollution Control Agency was a big one, the Superior National Forest, and quite a few other actually collaborators that collected field data for us. And we're actually able to get a pretty good data set to start calibrating some models. As I said, we had the original one. We used the old surface reflectance product, and that actually didn't work as good as the new one. The new ones actually work much better. So here we have the main, and then the aero surface reflectance. We used the random forest and more of the machine learning type techniques to figure out which band combinations to use, and we actually come up with a pretty good band combination to use for our models, and it seems to work really well over lots of different conditions. And so we're pretty happy with this model. Again, the main works a little bit better than the arrows, but both of them do work. When you look at the error, what we find is as CDOM increases, the errors go up. You can, that previous slide with the atmospheric correction, there's more error there. That is one factor that attributes to that. The other factor is that there's still, even though we have a lot of collaborators collecting this data, the data is very sparse yet. There isn't really a lot of CDOM data out there. So our window is actually 30 days, whereas with chlorophyll, water clarity, it's 1 day. So that's a pretty big swing. And the idea by using the larger window was this factor is very stable. And that's what a lot of the papers said, and some of the data that we had, that's what it indicated. But what we have found in a lot of these flowage systems, where they're connected to these big wetlands is the CDOM can change drastically. And that's what we noticed up in 2016 when we're collecting all this data. And so I think that attributes to some of this error that we have on that. So we were able to make maps. So we developed maps with the 5 different images from 2 different years. And then we used some of those images and other images to come up with water CDOM maps for 2015 and then 2016. And if you look at, kind of keep an eye, they are changing a little bit here. And big change in 2016 from 2015. And when we look back at that, we looked at the precipitation, found the 2015 was a fairly normal precipitation year, whereas 2016 was very wet. So it's up in the 90 percentile, 95 percentile. So we attributed to some of the pushing of the CDOM into the lakes from the surrounding wetlands. So here's a 2015, the mean from both of those, and we're looking at the distribution at the different ecoregion levels. And what we find, we have fairly moderate to low in the agricultural areas, and then higher up in the northern lakes of forest and the Minnesota, northern Minnesota wetlands again. There's a lot fewer lakes up in the northern Minnesota wetlands, but still some very high ones. We found that there are a lot of these really high ones, and there was some concern that there shouldn't really be a lot of high CDOM lakes in these agricultural ecoregions, and we really didn't study a lot of the actual wetlands itself, where it's really hard to get in with all the vegetation on them. So what we did is we just removed all the type 2, 3, and 4 wetlands out of the data set, and then did our analysis that way. We were able to remove a lot of those larger ones that were over here and maintain them over in the other parts of the state. And did this for our other analysis. And so all of our high CDOM waters tend to be up in those, and the counts are all different. So it's a little bit, hard to tell exactly how they compare, but you can see where they're distributed at. And so really what we're interested in how they change from these 2 years. And what we found is there's a big, actually in the agricultural ecoregions. So we use a threshold of 3 absorption at 440, and we found about 7% of our lakes had decreasing CDOM in the agricultural ecoregions, whereas the northern Minnesota ecoregions had increases of 31, and 23% of the lakes had increases of 3 or more. So let's see. With this research, we have prepared a number of different papers, some to do with the processing and methodology and stuff, and others to actually more applied to things like the chlorine demand and disinfection, byproduct formation potential, the iron's influence on dissolved color, CDOM is a proxy for dissolved organic carbon, how accurate is it, or how useful is it, and then things like the photo-produced reactive intermediates for water treatment, and then the stocks paper looking at dissolved organic matter in stocks with John's work with getting the volume of lakes and then trying to figure out how much dissolved organic matter there is in these lakes. So lots of different papers came out of this research. So with all this, so basically now with the automated system, we're going to be building this new enhanced data. So that's kind of, this is still in the works, but hopefully maybe this summer, hopefully we'll have something up. And as you can see from this animation down here, and then the graph, how lakes can change pretty drastically from one month to another. And so that's the kind of data we're going to have in this new system versus having it every 5 years. So it's quite an undertaking, and we're pretty excited about it, being able to do this. And The other thing we're moving is validating our models in other areas. We have some pretty robust models, and so lately we've been testing them in other areas, South Dakota, Wisconsin, Iowa, Florida, California, where else been? All over. Belize. So I've been doing these models a lot of different places, and works pretty good. Seems to work out. And with that, I have a bunch of acknowledgments, and with that, I can take any questions if you have any.
Let's thank him first. And then. Oh, question. Okay, well, so I worked a little bit on the late volume paper, but I'm still not up on CDOM.
Yep.
So you say that, I mean, you were showing that CDOM is low in the agricultural areas and high in the other areas, and that's just because there's higher organic in the soils, and maybe more, in the agricultural areas, you remove the organic matter because you're harvesting the crops, and it's just not as much organic matter available, or what is that?
That's my assumption.
Okay. So I'm guessing right on that.
Yeah, yep. They seem to be, with that area, I think it was more dilution. With the extra rain, it's more dilution because there wasn't you don't have the large wetlands, whereas up in northern Minnesota, you have those large wetland complexes. And if you look at, if you go to our lake browser and go to Upper Red Lake, there's a stream that comes in there that has big CDOM floats. You can actually see that in our CDOM maps that are on our lake browser. And you can see that pulsing into the lake. But that's coming from this large wetland complex flowing into there. Same thing with Lake of the Woods, the Rainy River. About halfway from Rainy Lake to Lake of the Woods, there's another river that comes in there that dumps a bunch of CDOM into the river. So by the time it gets to the Lake of the Woods, it's actually, that 4 Mile Bay has lots of CDOM in it. And it doesn't in the other lake, part of the lake, and other places are the same thing. So, yeah.
Are you talking about this in terms of climate warming?
Absolutely.
What's the?
That temperature thing looks like, there seems to be some trends here. If you look at that one,
I meant with the CDOM.
Oh, the CDOM. That is we need to do more historical stuff. I think we kind of dropped the ball on doing historical CDOM with Landsat, but that is something that we're interested in doing.
Well, there's a connection between the two.
Yep.
We do know that in very cold areas, as the Arctic melts and stuff, we're getting oxidation of organic matter.
Yep.
And such, the methane and other things. And presumably we also get more dissolved organic matter. But it seems like as it warms and gets shorter winters and longer growing seasons, longer warm periods.
Yep.
You might be oxidizing more organic matter, or at least partially decomposing organic matter. Then you flush it out during the wet year.
Yep.
And keep that cycle going. But it seems like you might be, for quite some period of time, as you warm, might be flushing organic matter out of, not the real recalcitrant stuff, but the sort of in between, not readily oxidizable material out. And at the same time, that would create contribute nutrients, which then goes to your, it's the mechanism of your warming trend, possibly.
Right.
Oh, absolutely. You're getting release of nutrients that had been stored in the watershed, and now are just, as you increase temperature, get a little bit more broken up, or at least the newer material, doesn't sit there as long. Like you drop leaves,
right,
and it goes into the substrate. If it's not, it may not be the really old organic matter, at least a relatively fresh organic matter, a larger fraction is decomposing and releasing nutrients that it did in the past.
Right, and again, like Finland and stuff like that, they have seen a big increase. They attribute a lot of it to the improving air pollution, I think the sulfites or something. So they actually had less acid rain, so then the lake's brown because of that. Was one of the
that would certainly be the case.
yeah. But yeah, I think that is definitely one of the things we're looking at, and with the automated system, we should be able to do, you know, some more historical stuff. Would be great to go back and do the archive of, you know, all the imagery and start to process and see where things are actually changing. It's the older imagery is harder to work with than the newer stuff.
Yeah.
It's a lot less more noisy, but it does work on that. So cool. Yeah.
Is there any evidence that at least in your populated areas, the higher salt content of waters might reduce population?
I haven't really looked at that yet. That could be. I mean, I don't know. You might have a better answer on that.
Well,
you've been looking at that.
The salt levels in lakes, at least, even in the urban area, aren't that high. They're not, there's about maybe 80 lakes in the metro area that are above the 230 milligram per liter criteria. But I think for population, you can go quite a bit higher than that. But certainly in stormwater, you know, pulses of stormwater, we can see concentrations in the 10,000 range for brief periods. So I don't know. Maybe it's a cyclic thing. You know, you get a pulse and then affects some organic matter and goes back to normal or something. I'm not really sure.
Yeah.
I don't know if like your analysis was like looking at like more smaller scale, but I've been noticing that some of these lakes that are seeming to turn more become less clear and have more CP around. Are they reverting back to? Are they going back at all to clear water state, or are they kind of maintaining that?
Since we've only got 2 statewide maps, I'm not sure, but that would be definitely something to look at to see how things are changing. Example would be the Sturgeon Lakes chain, or the Side Lake and Sturgeon Lake up by the north of like Ely, or not Ely, but Chisholm area up there. It's basically, you have South Sturgeon that's pretty much always dark, but those levels went from like 10 to 24, 25. So they're actually changing due to the pulses coming in. But that, like the next lake is, I forget, they name them kind of weird, so I get confused which one is which, but there's a Little, I think it's Little is the next one, and because it's littler than the other Sturgeon Lake. It's Little Sturgeon. And that one is, you know, the first year we did it, it was really clear. And then the next year when we had this more rain, you know, it pushed it through, so it became lots of CDOM in it. So it changed quite a bit when they're in those flowage systems, because you have these big source. So I don't know on a local scale how much they're changing, but that's definitely something we're interested in looking at. So, yeah.
Do aquatic or terrestrial wildlife populations seem to have any type of impact?
Does on the CDOM or on the water quality? I'm not sure about that.
Maybe like higher fish populations would result in less clear water.
Oh, probably not from CDOM, I don't think, but maybe. Yeah, I'm not.
Beaver ponding might.
Beaver
But I
ponding.
don't know if that's changing. It certainly affects, well, at least I'm not certain, but observation is beyond the boundaries.
Yeah.
Beaver ponds. I don't know if beaver ponds were originally high DOC or they caused it. I think to some extent they caused it.
Yeah. So yeah, I don't know. That's definitely some more research could be done on the subject. I think, yeah.
Along the line of that last question, I've been curious about the variability in any of the quantities that you've been measuring.
A lot.
I mean, you got,
so
yeah, some of those bars are pretty wide, and I'm just wondering about what's causing the variability within a given region. So you have the central forest.
oh, right.
Okay, so if you just took one of those and related to the last question, you know, what might be the factors or the processes that are causing that variability? If you were to take all the lakes, let's say in the central forest area,
Yep.
And you were to map out the contributing area to it and look at soils, vegetation, other kinds of things, whatever they might be, to see how they might be different from each other, and see if you could see if there's some factors that would fall out that would determine this one's going to be way up here on the, or on the range, and this one's going to be down here. Is that something?
Yeah, I mean, basically, it's pretty much the wetlands is the big factor, and lakes are very complex, and every lake's different, so it's a very complex question, and the hydrology is very complex in a lot of these lakes because a lot of them are connected. So it's a definitely PhD material, or 2 or 3 PhDs.
I know if the bog, what's the bog study up north? I think it's Sandy Bear that was studying years ago. I can't remember the name of it now. It's a Forest Service study.
Yeah, you're talking about at the.
What's the name of the place?
Now you're testing.
Marcel. Yeah. Is that continuing? Are they continuing?
Oh yeah, there's more and more going on. They actually have.
The hypothesis, you would see it with at Marcel, if anywhere, because that's that's just a bog.
Right.
And so you get kind of a pure signature there. You'd expect the DOC and the characteristics of that DOC to be changing. A pattern that kind of matches this.
I think Pat was looking into that with some a student, but they had a bunch of DOC data from the Mississippi River, and so they did that over like 100 years or something. So there might be an interesting paper. Pat would probably have some good information on that, and then they also gathered as much CDOM and dissolved organic carbon data that they could find in all these different stations, and looked at some of that. So they did. There were some areas that had improvement. It's not like, I think in Finland there are some, where it's obviously changing. There wasn't quite that effect here, but I think there were definitely some changes. But Pat would be the guy to actually get a good handle on it. I should get more involved with that.
I'd just like to add that we do make our data available online, statewide maps. So, just ideas from a perspective, PhD thesis or master's thesis. So, dive into the archive of data that we have to investigate those research ideas.
Yep, and they're all available on our website at lakes.rs.umn.edu. Zoom around the state and look at some like the Upper Red and some of those interesting. The CDOM maps are pretty interesting, and compared with the water quality, everything's interesting. So, yeah.
You had a bit of Lake Superior highlighted on your map earlier, on where you can see on trends.
Yep.
Do you have data for the entirety of Great Lakes, or at least entirety of Lake Superior?
Let's see. Wait, that's the wrong way. So you have more, we can do them. We can do it for anywhere in the world if you have an area, but let's see. So we have chunks of it, I think, in what you're probably looking at, right? Right there. Oh, there we go. So that, yeah. So we have, it's just, that's water clarity though, that's not the right one. I don't have like pixel level maps. I do have some pixel level maps that have CDOM, which I probably should have showed here. But they're online. I don't know if I can go online. Where's that? Let's see. Oh, I'm probably going to mess up the whole thing if I do that. I might.
No, whatever it should show.
It should show whatever I'm
As long as
doing.
you don't stop the sharing and stop the connection.
Okay, let's do that. Let's try. Let's see. X.RS. Let's see. Okay, so here's our lake browser. We can turn on our CDOM here for pixel level. It's going to come. Where is it? There it comes. So we do have part of it shown here, but let's see.